And hello YouTube, welcome back. We're going to continue our discussion of the kOmegaSST model. And so in the last video we were talking about some wall functions for k and omega in the viscous sublayer region and the turbulent sublayer region. So let me go get a handy table out. So viscous sublayer, intermediate, turbulent sublayer. Alright, then I'll have a k plus here, and then I'll have omega plus or omega star plus, and yeah, that's how I do it. So let's get this k in the viscous sublayer is this equals 0 as c k equals 0. Okay, intermediate, we don't have something there yet. In the turbulent sublayer, it is this. Okay, omega, it's here in the turbulent sublayer, and yep, what else? We have omega in the viscous sublayer. Where is it? Here is the viscous sublayer, omega. All right, and if we want to have a root, we want to have that in the intermediate region. We look at the root mean square, which I think I'll just write omega star, oopsie, omega star plus equals the square root of omega star plus squared in the viscous sublayer plus omega turbulent sublayer star plus squared. All right, so that's how we deal with it. Okay, so in the intermediate region, of course, we can have k as follows. I'm not going to go too much into detail, but here is one. Okay, so where are we? Yeah, this will do. Okay, so we use this omega star plus. Okay, k plus equals to omega star plus. Omega star plus, you can get it from here. Nu t plus, you can get it from here. This expression here. Then you have your du dy plus. So what is the du dy plus? We can either use Van Driest model or whatever. We can, yeah. Okay. So this is the log law du dy plus, and then other than that, this is equals to 1 in the viscous sublayer. All right. Okay, so in the viscous sublayer, du dy plus equals to 1, or you can use Van Driest model. Okay, so this sums up, how we can sort of estimate our k plus and omega star plus values in the turbulent sublayer, intermediate, the buffer zone, buffer layer. All right, this is called a buffer layer. Ooh. Buffer layer and the viscous sublayer. Okay, so that's how you compute k. I'm not going to combine this into one neat equation, but all right, why are we doing all this? It's not just to oops, sorry. Yeah, that was unintentional, but okay. Anyway, yes, I would like Yeah, so anyway, we want to go for viscous sublayer. No, we want to look at the blending function, how this blending function behaves in the viscous sublayer, etc. And how it behaves in the log-law region. So hopefully we can find an expression for F1 based on these wall functions. That's the whole idea of this. Okay, so let's go to this. What are we looking for? Yes, I'm looking for the original blending functions, which are here. All right. Okay. So these are our functions. Okay. So first we want to non-dimensionalize them. We want to non-dimensionalize them so that we can get these functions as a function of y plus. So these are dimensionless distance from the wall. That's what we want. And how do we find that non-dimensionalization? How do we non-dimensionalize all of this? Okay, so we go to here. Okay, so look at k plus equals k over u star. K or k plus rather equals to k divided by u star squared. This is a friction velocity. Then what about omega? Omega star plus. Okay, so all these are usually written in omega star kind of a manner. Okay, these are omega star plus. So this is equals to omega star nu divided by u star squared. So I'm just going to use omega star from now on, right? Because that's how the CFD codes and the guides usually write it. Okay, so with this we still have one more. Then y plus equals to y u star divided by nu. Okay, so this is a non-dimensionalization. With this we are able to deal with our first term. Okay, so the first term is this. So we have square root of u star squared into k plus. Omega star is at the bottom, so I just copy and paste that here, or rather omega star plus, all right, u star squared divided by nu. Okay, divide by nu. And then y will be equals to y plus times nu divided by u star. Alright, so let's see whether all of these cancel out. Okay, so the top will be square root of k into u star. Or rather, I'll just use this to copy and paste here, it's faster. And the nu's cancel out. Okay, the nu will cancel out. And this will cancel with this. So I'll just have a u star at the bottom. And basically, it looks like most of these actually cancel out. So we just get this nice, very nice dimensionless number. Okay. And now with this, okay, we can non-dimensionalize. Alright, now with this, it's easy to, we can substitute in. Okay, so what can we do here? Okay, so let's get this table here. Or rather, okay, yeah, we can substitute this in using these functions above. All right, and how are we going to get these functions? Okay, how are we going to get these functions? We just look at the table here in the viscous sublayer and the turbulent sublayer. Oh, turbulent is turbulent sublayer, and we just do that accordingly. Okay, so anyway, I just want, yeah, I want to put all of this in Excel, of course, and let's see how these actually evolve. All right, so we open our Excel file. This was our old planting function to see how this hyperbolic graph actually works. So I want to have a value of k plus with respect to y plus. So I'll have a column for y plus first. Then I'll have a column for k plus. And then omega plus. Or omega star plus. Okay, so that's where I'm going to start. Okay, yeah. Y plus, k plus and omega star plus. Now, for simplicity, I'm going to ignore this buffer layer because if you look at the log law of the wall, okay, you look at the log law of the wall, you can see that the true curve being the red curve over here, the true curve being the red curve, this is the proper function, but actually it's pretty well approximated. The trend anyway is sort of approximated well by these blue curves, and the blue curve here, this one is the log law, and then this blue curve here is the viscous sublayer. So I'm not going to do too much on that, but yeah, so we can have two functions to approximate this. All right, this function, which is the log law of the wall, okay, 2.5, okay, and let's go. Whole function is here. So these are just approximations, just to get us quick results. Okay, so we can use these equations here to sort of approximate what's going on. Alright, so 11.6 is this magic number, but there's nothing really magical about it. So let's put 0, 0.5, 1.0, and we go all the way to 11.6. So 11.5, 11.6, 12, and we'll pull this up all the way. So in the log law region, I think I want to have like less data points. So 12, 20, 30, 40, and we'll go all the way to 300. Y plus equals to 300. Okay, so that's that. For the sake of good comparison, we'll just have a U plus here, and in the viscous sublayer, U plus equals to Y plus, and I'll just put it there. Okay, I'll put it to 11.6, and here is where I want U plus equals 2.5, so equals 2.5 times ln of Y plus 5.5. all right, and then I'll go all the way up to 300. Okay, So that's the U plus part. I'm just doing it a very simple way. Okay, so here in the viscous sublayer, K is 0. So equals to, I'll just put CK equals to 0 then. 0 times y plus to the power of 3.23. It's kind of redundant, but I'll just do it for sake of, completeness sake, so to speak. Okay, and once you're in the turbulent sublayer, this kind of takes over. So K equals to 1 divided by square root of 0.09. So there's some sudden jump here, but it kind of gives you the rough trend. So this is an approximation, this is not the real thing, but it gives you the rough trend anyway. Okay, and here omega, okay, equals to 6 over this, over y plus squared. Of course, at y plus equals 0, this actually shoots up to infinity. So instead of that, I'll just put 0.001 here and to approximate the wall. So this omega equals to 6 times beta 1, or 6 over beta 1 equals 6 over beta 1. And what is beta 1? Okay, so let's just put, okay, just for clarity's sake, C mu equals to 0.09. Beta 1, let's take a look here. Beta 1 equals 3 over 40 over here. 3 over 40. 3 over 40. Alright. So beta 1 equals to 3 over 40. Okay, just for, and also to help here, you can use a kappa. Kappa equals 0.41. C mu equals to 0.09. Alright, so let's just put that for getting the trend. So 6 divided by, okay, 3 by 40, okay, 3 by 40 times y squared, y plus squared. Okay, so it's horribly big at the start, and it will rapidly shrink all the way here. Okay, so it will go down as such. Okay, so I just put the 3 decimal places there. So you can see the dissipation rate is very, very high in the viscous sublayer, but rapidly decreases. That should be expected. Okay, so I'll just delete this off. Then I have the turbulent sublayer as a 1 over y relationship. So just so happens this is k plus over times 1 over kappa y. So equals to k plus, because this is 1 over c mu also. I'll just do that. Times 1 divided by, or rather divide by kappa, which is 0.41 times the value here, y. Alright, so 7.01, and then you just go all the way down here where the viscous dissipation gets less and less. Alright, so this is based on law of the wall. Based on law of the wall. Okay, so now we have this, it's easy to get this function. We get this first function, square root of k, or square root of k plus over omega star plus times y plus. So square root of k plus divide by omega star plus times y plus. Okay. Okay, let me do this and put this here and close it here. So equals to square root of k, which is 0 here, divide by omega times y. So that is 0 here. This will remain true all the way through, whether it's the viscous sublayer or turbulent sublayer. You can see this value just takes a jump from here. Okay, so it looks like this is yeah, it looks like this is just 0 here in the viscous sublayer, jumps here to 0.22457. Okay. Alright, so we can stop for now, and then next video we can take a look at these two other things, then we can kind of get a trend. Okay, so thanks for watching, I'll see you guys again. Bye bye.